Welcome. In this sixth lecture we cover calculus. What is calculus? The common definition is that calculus is a theory of integration and differentiation. It is certainly also a theory of limits. A bit more general, maybe even more approachable, is to say that calculus is a theory of sums and differences. It is a more modern definition also, as it includes combinatorial versions. When including limits, one gets then as a limiting case the integration and differentiation. Calculus has a huge cultural background. The subject ranges from pre-calculus notions like functions and limits to length and area and volume computations, and then to the analysis of motion. Together, integral and differential calculus allows to predict the future of an event by first using differential calculus to find the law, and then use integral calculus to find the solution. Here are some pioneers in calculus. Maybe you recognize some faces. We will talk about some of them today. And here are more faces. Each is related to a story, a theorem, or a whole theory. You will pick up in your project a person from each millennium. There is a treasure trove of history and drama to be explored. How could one summarize calculus in one tweet in 140 characters? Here is an attempt. So if you take the function fx is equal to x to the n, then differentiation gives you n times x to the n to minus 1. And integration gives you x to the n plus 1 over n plus 1. Knowing this captures an essential part of calculus. These are functions which one can differentiate and integrate. The two operations reverse each other. One picture summarized is in this picture, also a cartoon book of Larry Gonick. The book is highly recommended. It certainly avoids the bloat we see in many calculus textbooks today. Why do we want to learn calculus? I once made a little clip, 10 reasons in 30 seconds. Ed Berger summarized calculus once in 20 minutes. It's a highly recommended movie. You find it on YouTube.
So what do we do?
Let's try to explain calculus in a way how the Greeks could have understood or developed it. There are two operations, a summation and the difference process. If you look at the sequence of numbers like 1, 1, 1, 1, 1, it can be summed up, leading to the concept of digits. Taking differences gets us back to the original sequence. Let's now think of the strings of ones as marks, like on the Ishango bone, not as marks on the Ishango bone, but as a constant function 1, 1, 1, 1, 1. And the summation function is again a function. It corresponds to the function fx equal to x. And then we can continue. So legend goes that Carl Friedrich Gauss, as a 6-year-old, once got the task to add up the numbers from 1 to 100. He immediately wrote down the number 5050. How did he do it? He paired up the numbers, took 1 plus 100, 2 plus 99, 3 plus 98, etc., and got 50 pairs of 100 and 101. So he said, here Ligatzi, here it is, and to his teacher, Mr. Butker. Anyway, what Gauss did is to do an integration process. He added up the integers and got a new function, a sequence of numbers growing quadratically. It is the function n times n minus 1 half. But we can look at it differently. We see the addition process as an integration, and the subtraction brings us back to the old function. 28 minus 21 is 7. The numbers which Gauss constructed are called triangular numbers because they compute the area of a triangle. We can continue now like that. Adding up the triangular numbers leads to tetrahedral numbers. We now grow in a cubic way, like the volume. So if we stack triangles onto each other, we get the volume. What we have done with this summation process is found a formula for the volume of a discrete tetrahedron. I once summarized all calculus in a talk of 20 times 20 seconds. This format is called Pecha, where 20 slides are shown in 20 seconds each, with no mercy on time as the slides go automatically. You find that on YouTube too. So 20 times 20. It's a highly recommended format also in schools. So the upshot of this talk is that if the Greeks would have known the concept of functions, then Archimedes could have developed calculus, the entire calculus, already then. Here are two books which are recommended. I already mentioned the cartoon guide of Larry Gonick. There's a nice little book also, How to Ace Calculus, which is cheap and short and up to the point. And this is the end. In this part B, we try to make some advertisement for calculus. Applications are always the best motivation. One of the main goals of calculus is optimization. Another one is to compute area and volume. A third one is to understand motion and predict how the motion continues. Fermat realized first that at a maximum or minimum a function should have a tangent which is horizontal. This is an important observation as it will be accessible to analysis. So here is an example. Find a rectangle which has maximal area if the side lengths are x and 1 minus x. We can define the function fx equal to x times 1 minus x, which is the area of the rectangle. Then differentiate it and look where it is 0. This shows that the square optimizes that problem, x equal to 1/2. Things can be more tricky if the function is not smooth. Here we see the Weierstrass function. Weierstrass looks indeed a little bit worried on this picture. Well, there is no tangent defined. Let's look at the nice application of calculus. This is catastrophe theory. It can explain, for example, how conflicts appear or friendships break down or other discontinuous events happen. It is still all calculus. Here's a simple example in that theory. We have a function and deform it. There are two minima initially, then only one. The stable situation jumps discontinuously. Now it's on the right, the equilibrium was on the right, but then when the equilibrium disappears, puff, the ball falls down to the other equilibrium, and this change is discontinuous. So it's an example where you have perfectly smooth situation, everything is differentiable, but still the minima change discontinuously. Here's an application of that theory to perception. So look at the dude here. As the picture deforms, we see that the dude first, so if it deformed, we see the dude first, and there will be a time when the picture flips and you start to see a kneeling woman. I think for me this about happens here. So now we have a different view, and we can go backwards. And when you go backwards, you see the kneeling woman. But there will be a spot where discontinuously your brain changes and doesn't see anymore the woman, but suddenly sees again the dude. So this is completely analog to the ball jumping picture we have seen before. It doesn't even have to be a deformation. In this picture you can see both an old woman looking down to the left. The nose is kind of what you see there. Or you see a young girl looking right up to the left, and her chin is what has before been the nose. If you look at it long enough, you are able to switch forth and back between the two minima, the old woman or the young girl. So here's another example. If you look at the dancer, a dancer to the left, the middle dancer turns one way. If you look at the dancer to the right, the same dancer in the middle turns the other way. Now if you change your point of view, you move from your center from the left to the right, there's suddenly a change happening, and this is what one can describe with a catastrophe. So here's an application of calculus which is quite practical. If you sit at a table with four legs on an arbitrary surface, smooth but not flat surface, then in general it wobbles. Not all four legs are on the ground. But there is a corollary of the intermediate value theorem which assures that you can turn the table in such a way that all four legs are on the ground. This theorem is usually, considered the boring part of calculus. It's obvious, right? Somewhere the function is negative, at the other point it's positive. Of course it will pass through zero, but it has a nice application here in the wobbly table theorem. So here you see an animation. So we have the three legs on the ground, and now at some point the fourth leg will be exactly on the surface again, and it's just the intermediate value theorem which assures this to happen. Also, music is actually just calculus, because a piece of music is a function. So that it gives the amplitude of the sound at a given time. We can plot the function, but we can also hear it if we listen to that function. In number theory, calculus plays an important role. So here's a example we have already seen in number theory is the Goldbach conjecture. Every even integer larger than 2 is the sum of two primes. You can completely describe this using calculus, define a function, and then you square it, and then you look at the derivatives of the even derivatives of fx squared, and if they are positive, then you have proven the theorem. This problem, the book stacking problem, is a problem you will work on in the homework. It's a quite interesting riddle. So if you have stack books onto each other, the question is how wide can the bridge be? And the surprise is that whatever distance you want to bridge, you can really do it like that. So the rules are that the books have to have the center of mass of the books have to be on the table. It's really surprising that you can you can reach over that. Here's the answer how you do it. You do it in a kind of non-obvious way. You start very small. If you have 4 books, like here, you start with 1/4, and then you add 1/3 and 1/2 and 1. So you have this harmonic series which is known to diverge. Differential calculus was motivated heavily looking at the heavens. It was especially Galileo who started to analyze and understand gravity. Here is a clip from the Battle for the Heavens movie that describes how our solar system moves. So this is described pretty well in an older show by Carl Sagan. Another application is that pi is irrational. There's a quite simple proof using calculus. We have seen that the square root of 2 is irrational. It was pretty straightforward to do, but to show that pi is irrational, that needs a little bit more using the fundamental theorem of calculus. And that's the end of part B. In this part C, we look at protocalculus. In particular, we look at 2 problems. The problem of limits and the problem to find the volume of the sphere. I call this protocalculus as it does not yet involve the interplay between differentiation and integration. But these still are the seeds of differentiation and integration. It was Zeno who was a pioneer in the question about limits, and Archimedes who spearheaded integral calculus. We look at these 2. But there were others who were involved in protocalculus before Newton and Leibniz. An entire book of Arnold describes the role of Huygens, Barrow, and Hooke. The picture shows Huygens. The concept of limit is not easy. Zeno worried about it first. We see him here leading the way, searching. Here's one of his paradoxons. Zeno imagines a race between Achilles and the turtle. We don't know where Zeno is running to here, but maybe he tries the paradox out, playing the role of the turtle while one of his pupils is Achilles. Anyway, here's the story. Achilles gives the turtle a bit of a head start, but when he reaches that point, the turtle has moved ahead already. And so on. Achilles can never reach the turtle. Another paradox is the arrow paradox. How can an arrow which is fixed at every moment move at all? This paradox might also have been a nightmare of Zeno. Maybe they came from a nightmare, he being chased by Achilles, shooting arrows at him, and his intellectual relief was Achilles can never reach him, and the arrow cannot fly because there is no motion. An XKCD cartoon here explains this. These cartoons often need a little bit of background. So also the poet T.S. Eliot might have thought about Zeno when stating that history is just a pattern of timeless moments. Eliot was a Harvard graduate. So let's look at Archimedes. He solved an important problem giving the volume of a sphere. So he's considered today the father of integral calculus. First of all, the Greeks already understood how to compute the volume of a pyramid. We try to illustrate this proof using 3D printed objects. For a pyramid, we have to understand
the architects
the volume. Here is another visualization attempt printed out in ceramic type material and an animation showing why the tetrahedron formula holds. For the sphere, one needs another idea, and Archimedes got it. So his argument was to compare the area of a cross-section of a sphere with the complement of the cross-section of a cone in a cylinder, and adding up the slices gives them the volume of the half sphere, in this case 2 pi third. We once produced a drinkable proof of this. So you can fill it with water on top. This is the volume of the half sphere, and then below you see the complement of the volume of a cone inside a cylinder. We could make a nice statue fountain on the Science Center piazza. So here's a clip from Nova about Archimedes. Finally, we can ask the question whether limits are actually needed. And there are versions of calculus and versions of physics which do things completely in the discrete and don't involve the concept of a limit at all. I keep a blog about this, quantum calculus. This is the end of part C. In this part C, we look at the fundamental theorem of calculus. Understanding this theorem is equivalent to understand calculus. Galileo stressed how important mathematics is in understanding nature. There are two concepts. One is the process of analysis, the other the prediction. We know that in daily life, in order to predict the portfolio of an account, we need to analyze its behavior in the past. The first concept is to look at differences to understand the rate of change. Here is an example from the textbook. In order to understand the slope of the tangent at the parabola, y is equal to x squared, we need to take limits. In this case, we see, however, that the limit is easy, as there is a cancellation of the small number h. The limit when h goes to 0 is then just 2x. We can see a sum as an area under the graph of a piecewise constant function. It's a Riemann sum. If we take the step size h smaller and smaller, we get the area under the curve. Working out the sum is sometimes possible, like here, but brutally hard in general. Here's the first part of the fundamental theorem. If you add up the differences of a function, we get the total difference. The second part tells that if we take the difference of the sums, we get the function back. These basic and obvious facts will, in the limit, become the fundamental theorem of calculus. An important point is that we can now compute areas by knowing about rate of change. It's a fantastic tool. Finally, let's look at the question who invented calculus. Archimedes is the father of integral calculus, and Fermat should be considered the father of differential calculus. However, Newton and Leibniz both should be credited to find a relation between the two concepts and to apply it. Here's the obligatory XKCD cartoon to this. There indeed has been a priority dispute, described in the story of math, and this is the end of part D. In this last part, E, we try to have some fun with sums. It is not an easy topic. We will see that the most famous of all open problems in mathematics deals with sums. Our host is first Henri Poincaré. He invited the reader once to look at two sums. The first is the sum of 1000 to the n over n factorial. The second is the sum n factorial over 1000 to the n. Let's experiment with this for small n. First to the first sum. Here is what the computer shows you when you sum things up to n equal to 20. Seems to grow pretty steeply. But if you go further, like 35, you see that the initial growth had been misleading. The sum actually converges. The limit is e to the 1000. It's the exponential function, Taylor expansion of the exponential function. Now to the second sum. It looks nice at first. We sum up 20 first terms. There's a growth, and then things flatten out. But this was deceiving. There's a growth again. Actually, you see that if n reaches 2000 already, then each term of the sum is larger than 1. The sum clearly diverges. So numerical experiments can be deceiving. Here's an example of a convergent series. It is a geometric series and related to Zeno. If you take 1/2, then 1/2 of the remaining 1/2, then 1/2 of the remaining 1/4, etc., you get a limit 1. Formally, you can see this. If you multiply the sum s by 2, then you clearly get 1 plus s, and you can solve for s and get s equal to 1. If you replace 1 to the 2 to the k but with 2 to the k, you clearly get a divergence series, but mathematicians still can make sense of it. Actually, the sum can be given the value -2, because you have an explicit formula for s and evaluate it for s equal to you get S equal to minus 2. One calls this an analytic continuation. There is an entire book about this by Hardy. Divergent series are not nonsense. They are important in number theory, especially in the context of the zeta function. The sum expansion of this function only makes sense for S bigger than 1, real part of S bigger than 1, but the function is defined and finite in the entire complex plane except at S equal to 1, where we have the harmonic series. The proof that the harmonic series diverges is easy to do. You will prove this in one of the homeworks. Here is the zeta function evaluated at S equal minus 1. You add 1 plus 2 plus 3 plus 4, etc. It clearly diverges. Good luck convincing your friends, however, that the sum is minus 1/12. It has been known since 150 years that one can make sense of this, but only now in the time of YouTube and Numberphile that the general public starts to notice. It is the most important problem of all mathematics. It's the Riemann hypothesis. It claims that the zeta function has all roots on the line real part of S is equal to 1/2. Here I computed the first roots. Each strip shows part of the complex plane. It's a critical strip, but I turn it by 90 degrees. You see all roots are in the center of the so-called critical strip. Here is Bernhard Riemann, who made the conjecture, his manuscript, and here is his article. We look at this article in the homework too, and one of the problems will be to prove the Riemann hypothesis. This is the end of part E and the end of this lecture.